especially the path of development we pursued in this case. And since my background is to be found in material sciences as well, this presentation also represents the perspective of a material scientist, I think. So the view of a domain expert on the ontology development, or especially on our development of this ontology. So then let's go from a standard to an application ontology. And I just want to start with some words about standards in general. So some brief insights into standardization organizations and some hints or specialties about the content of standards, especially to show its complexity. And then I would like to dive into the tensile test ontology development with the collection of information and parameters and the way of their formalization. And in the end, there will be a very short demonstration of some little queries to our data. So in general, the primary function of standardization organizations is, of course, developing, coordinating, interpreting, or otherwise producing technical standards to address the needs of a group of stakeholders. And there are a lot of such organizations. They can be derived or differentiated by or classified by their role and position and the extent of their influence on the national, regional, and global standardization arena. So, for example, we have the ISO, which is composed of the national standard bodies, one per member economy, and which has established tens of thousands of standards covering almost every conceivable topic. And these standards are naturally evolved from those designed in-house within industry or by a particular country, while others have been built from scratch by groups of experts who sit on various technical committees. And it has to be mentioned that the existence of international standards does not necessarily restrict the use of other published standards. So they all coexist and might be in use. We also have regional and even sub-regional standard organizations covering regional aspects, of course, and nearly each country, as already mentioned, or economy, has a single recognized national standards body that is likely the sole member from that economy in ISO. And ISO currently has 161 members, just to give you a number. And finally, of course, there are some more technical organizations and associations which provide guidelines, recommendations, or standard operating procedures that mainly cover aspects of safety and quality in production processes, for instance. Such might not be standards in the proper sense, but might be counted to this field, and we have to consider them as well. So when building an ontology of a method or a process, in our case, in accordance with the standard, we always have to consider that there might be other standards with the same or very similar goals and scopes that might also be similar in procedure, but even though slightly different. And we always have to name the standards we are referring to, of course. So what does such standards look like? Usually after the definition of the scope of that standard and some references to other standards and documents, there's a definition of terminology and symbols used. And this is very helpful when defining and describing parameters and entities that lead to the definition of subjects, objects, and properties, as we already heard in the talks before, in our ontology. So this is a good start. However, it has to be considered that typically not all entities needed in such an ontology are defined here, and especially their relations, what they are needed for and how they interact are mainly given in the text body of the standard. And again, there are differences between several standards. So at least in wording of the definitions. So the reference is very important. It's just an example from the tensile test standards of ISO and ASTM. This also shows us that even using the same terms, so in this case yield strength, of course the definitions can be different in detail when communicating in material science, at least as already mentioned in wording. But sometimes even a single standard is hard to read or digest, especially when trying to build an ontology. Within the frame of technical restrictions, of course, a standard for a test method usually allows for several variations of test parameters, mostly under certain conditions. And all these variations, conditions, and requirements have to be considered in the ontology as well. And within the standard, all the information is given in a text body, of course, but there are also notes, footnotes, equations, and even references to illustrations and figures. And furthermore, specific methods are often described in the annex. So all this information has to be analyzed, and then this helps to understand and create the relations of parameters and entities that are to be transformed into an explicit ontological description. So there's a lot of knowledge in the standard that has to be represented, but also background knowledge is needed, which has to be covered by the ontology. And this is what we try to include in this exemplary tensile test ontology. So what did we do to get our information? All in all, we used the typical sources of information and knowledge to build the ontology, and these are shown here. So there are standards, or the standard in our case, which was the ISO 6892, and you might also think of some other scientific literature. We did some interviews with the technicians who actually do the testing every day to really get every step and every movement that is taken when performing and analyzing the test. Furthermore, information can also be gained from manuals of the testing machines, for example. And last but not least, of course, some personal expertise and experience can yield knowledge to your ontology. So especially when you are a domain expert yourself. And then we started this process. We already heard something about it, of ontology development, which I would like to call transformation procedure from my point of view as a material scientist here, and which includes the collecting of information and identifying the parameters needed in our process, structuring them and find categories for it. And then we use the visualization step to verify our structure in an easy way before we formalize it in a thesaurus in natural language. And finally, this was transformed into machine understandable web ontology language by using Protege. We already heard about this, but I will show it in some more detail. And according to these steps, I would now like to show some examples and the IT tools that we use respectively, because this might also be a question in this case. So we all started with determining and listing process relevant parameters. We collected them in classic spreadsheet tools like the well-known Microsoft Excel, or maybe you could also use LibreCalc as an alternative. And then we found categories and subcategories, which are here, for example, the nominal parameters and the measurements as the main categories, and then the initial parameters or equipment parameters as subcategories. And to get the syntax and the semantics in, we defined, of course, the symbols and units in accordance with the ISO standard, of course, that are perfectly given there, and references to the glossary, including the definitions, of course. And it's also possible to use a visualization tool, such as some MindJet or some other mind managers for this task at this stage already. Probably if a classic listing of parameters is not wanted. But yeah, anyways, for the creation of a taxonomy, so the classification of concepts and hierarchical process flow, a visualization is recommended. And this was also used in our case. And this could now be done by using the aforementioned mind map tools such as MindJet. We can see an example here on the right-hand side, or there are also online tools such as the knowledge base builder by InfoRapid. And this knowledge base builder also allows for taxonomic representation in a typical form of such a tree, and entities are marked with different colors. So therefore it seems to be very suitable and convenient for the ontology modeling of processes and methods especially. And the tool is free, by the way, which is also a rather nice thing to say. So, but when trying to create such a taxonomy or to model such processes in an application ontology, there are always different possibilities to do so. We already heard about this as well. So especially with respect to the possibility to query concepts, classes, and properties. And here's just a simple example of classes. So you could say that a tensile test is simply a process and therefore connected directly with the concept of process, which would in this case even be in the core ontology of our PMD core, by the way. And this would perfectly be correct. However, there's not much additional or deeper knowledge in this representation. So you could also insert some subdivided processes and such further define the tensile test. So, for example, as an analytical process, part of which could be a test method that include destructive testing methods, and then there's the tensile test. And when such a structure and classification is developed, there are, of course, always some considerations that have to be kept in mind. So first of all, we have to ask ourselves if this classification is useful So will there be anyone who would or could want to query for the information that is given by such a new level? So for example, could a user want to query for all analytical processes that are in the ontology? I think maybe yes, this could be a good thing. And moreover, the classification should be correct, of course. So it might not be so good to ascribe the tensile test explicitly to a non-destructing test method. So of course, the knowledge must be correct in there. And it has to be considered whether two classes are only different in designation, but very similar in content. So if there's simply synonyms that would rather be represented by labels, for example. So in this case, you could maybe argue that test method and analytical process are rather similar. So you could maybe omit test method as an additional class and maybe use it as an alternative label for this analytical process, or set them to similar state. So this classification is also already mentioned, always depends on the perspective and what is meant to be represented within the ontology, and therefore it is a case-by-case decision in this case. And if all these decisions are made, the concepts, classes, properties, and relations are to be formalized in a thesaurus. That means definitions of entities and these concepts and the useful relations are given in natural language. And as IT tools, I think any text program or editor can be selected, for example, simply Microsoft Word. But for a collaborative work, as also already mentioned, platforms such as GitLab are recommended to have a commonly accessible repository and this versioning control and so on. So this is then very useful when working together, of course. And here's just a little example of our natural language representation with all the relations and, of course, the definitions of the entities that are given here. So finally, based on this thesaurus, all the considerations have to be transformed into an ontology using the web ontology language OWL or OWL. And therefore, the free tool Protégé, also already mentioned, of Stanford University is strongly recommended. By the way, I don't think whether there's another tool with such a functionality, to be honest. Of course, Protégé allows the construction of a hierarchical order of concepts and of rules, all in a Explorer-like structure. The knowledge about the relation of concepts is included, of course, and then it is also possible to deduce new knowledge by inference, or maybe at least to say it's possible to find relations between the concepts by using first order logics, which we all already knew about. So, and in the end, the created ontology can also, or maybe has to be visualized, at least for verification and validation. And therefore, the free web app WebVowel is recommended, which also enables visualization in such a tree-ish appearance. We also saw it on one of the last slides in the last talk. And yeah, this is also the point where I want to finish with a little demonstration of queries we can already run on our system. So we have this little Ontologie tool. Let me just switch gears here. Hope you can see it all. We can run some queries on that. So there is the ontology and some data of tensile tests already in there. And in this example, we will query our test data for the measured value of RPO1. So we just let us give the query would be give me all the tests that have a measured yield strength of RPO1. And if we do so, we can see, I will just put that in and give you the results, because we can see there are 12 measurements, of course, that have the RPO1 value in it. Then we can have a close look at it. And we see, of course, there's a certain identifier with it. So the URI of it and the yield stress of RPO1 is, of course, given in megapascals. And it's a literal, of course. And here we can see the value, and we can see this for all of them. Right, so there was one value and the next value, and that's possible for all the 12. You could also run it maybe for RPO2, which is a bit more ordinary maybe. Because RPO1 is something special maybe in Thiel's world, but of course it's the same. We've got the same 12 data sets, by the way. There are not many in it, but at least to show you that it's possible. We have a different value here of RPO2, of course, which is again a literal in the megapascals range. Yeah, so that's the way I want to conclude my talk, and yeah, hope you enjoyed it. And of course, I'm happy to ask or answer your questions if there are any. So thank you.